Is it a good, so first question, is it a good idea? To compute eigenvalues like this? And where we will have problems? Okay, good idea is like binary answer. What do you think, good or not? No? Anyone thinks it's a good idea? Well, obviously it's a bad idea. The next question is more complicated. Why it is not a good idea? What do you mean? Yeah, so how it's called in general? What is this? It's numerical instability, right? Relational factors. So where we will have errors, by the way? So where is the instability? So when we compute the coefficients of the polynomial, when we compute the actually computing, we'll discuss, when we compute the polynomial in one representation and another, can we do it in an accurate way? So for polynomial. So for polynomial, we in fact can do it in an accurate way, so the coefficients would be within some range close to the true coefficient. But actually, when we try to compute the roots of such polynomial, then even small perturbations in the coefficients of the polynomial may give you large variations in the roots. So if you have the standard representation of the polynomial in terms of monomials, as we all do, this is a very ill-conditioned problem. Computing the roots of the polynomial from the coefficients of polynomial is an ill-conditioned problem. Computing the eigenvalues of the matrix from the entries of the matrix is a much better conditioned problem. So small perturbations in the coefficients of the matrix leads, especially if this matrix is, for example, Hermitian, leads to small perturbations in the eigenvalues. But small perturbations in the coefficients of the polynomial may give a large variation in the roots. So this is the example when we have a good problem. Then using standard technique, we reduce it to a bad problem, and we lead to, this is an example of a bad algorithm. Okay, let's just see what happens here. So this is the Hilbert Cauchy matrix, but with minus here. So we compute eigenvalues. There is also a special NumPy function for computing characteristic polynomial, which gives you the coefficients. And there is also a NumPy function which computes the roots. We'll get back to it and then we'll just plot the eigenvalues. Okay. Sorry. So here there is no difference between orange dot and blue dot, so at least for 5 by 5 keys they are not distinguishable. But if you go to 10, for example, by the way, there is a nice distribution of the eigenvalues. The eigenvalues are complex. So remember, the sequel values, they are all very close to pi. The eigenvalues are different. They are located on some sort of a circle. That's also a funny thing. And still the same. It's still the same. Some difference appears, but not too much. Now you see the difference is starting between two sets. Yeah. So for example, go 40 by 40, we need to solve the polynomial equation of degree 41, and there is a difference. Right? So this is okay, this is correct, this is completely wrong. So that's the example that it's not stable. Now the question, how the roots are. Anyone knows how the roots of polynomials are computed? What this function has under the hood? You need to find many roots, right? So you need to localize them first, right? So it's not so easy. You need to find the interval where the roots for each root, and these are complex roots. So it's difficult to find localization. we have done, we have reduced the eigenvalue problem to a polynomial equation. We can actually do the opposite. We can take a polynomial equation and reduce it to eigenvalue problem for a certain matrix in such a way that the characteristic polynomial of this matrix is exactly our polynomial. This is so-called companion matrix. And then the roots of the polynomial are computed as eigenvalues of the matrix. So this function, it actually creates another matrix of, well, a simplest sort of diagonal plus some border there. So it's called companion matrix. And then compute eigenvalues of this matrix. So it's actually computation of, even the computation of the roots is done by solving eigenvalue problem. But unfortunately, since this problem of computing the roots from given the coefficient is a very ill-conditioned problem, a small perturbation of the coefficient may lead to huge perturbation in the solution, in the roots. This companion matrix has nothing to do with the original good matrix. So there are some remedies for that, because the monomial basis is actually here. So the monomial basis for polynomials, we are not going to discuss, but the monomial basis is, so what is a polynomial? It's a linear combination of monomials. So it's an element of a linear space spanned by these functions. These are very bad functions. So what's the ideal basis? The ideal basis is the functions that are orthogonal. For vectors. But for functions, we can also define a scalar product, for example, like this. And if you take a scalar product between two monomials, this is a Hilbert matrix, which is very low rank. So it means this basis is very bad. So even the way that we represent polynomials as a linear combination of powers, it's a very bad idea to represent polynomials. If instead of this basis we use, for example, Chebyshev polynomials or any other set of orthogonal polynomials, then this representation would be much, much better. So monomials are almost collinear, and you never use monomials. So the only case you use monomials is when your data is distributed on a circle. When the data is distributed on a circle, beta uniform, then the monomials they are orthogonal with respect to the scalar. But that's the only case. Otherwise, if you consider monomials on an interval, never. That's a very bad idea. And you can actually use very high degree polynomials if you use, for example, Chebyshev basis. But that's another story. Okay, so the moral is that that's a very bad idea to compute eigenvalues by solving characteristic equation, because the transition from the coefficients of the matrix to the characteristic coefficients of the polynomial introduces a large error in the roots. And in reality, when we need to solve a polynomial equation, we just write it down back as an eigenvalue problem. So just a few slides about so-called Kirchhoff circles, because, well, sometimes we need to localize, and we will need it further on, but here we just present it as a separate topic. So, even if we use some iterative method, we need to localize the eigenvalues of the matrix where the eigenvalues are located. So, and that's the theorem. So it's the example of so-called eigenvalue inclusion set. So remember, the eigenvalues, they are located on a complex plane, and computing eigenvalues, well, is sort of difficult. But if we can find the regions in a complex plane that contains eigenvalues, in some sense separate, we may use this information later on. So the theorem states that you have so-called Kirchhoff circles. So Kirchhoff circle, well, from the name it's clear that it is a circle. Sorry, let's mix it up. So you have the complex plane, and you have the matrix. So for example, A11, A22, A12, A21. And this can be complex numbers. So we put the center that is equal to the diagonal element. So A11, A22, and the radius is equal to the sum of absolute values of diagonal elements. So suppose we have a situation like this. So if we have two disjoint circles, then we can say that such circle so if the circles do not intersect, each circle contains only one eigenvalue. So in this case, maybe one eigenvalue somewhere here and another eigenvalue somewhere here. So if they intersect, so we may talk about the number eigenvalues, but the main statement is like this. So if you have this circle that does not intersect with any other, it has one eigenvalue inside. So that's the statement. So the proof is instructive because, well, it uses the strictly dominant property. So, and the Neumann series. So, well, there are cases where you have this. So the meaning of this theorem is very simple. If you have diagonal matrix, then the eigenvalues are located on the diagonal. If you have small of diagonal elements, small in terms of the sum of the absolute values, the eigenvalues do not change much from the diagonal elements. So they are located inside the circle with the radius that is bound. So the first lemma that we need, that if the matrix has this strict diagonal dominance property, is if the absolute value of the diagonal element is greater than the sum of all of diagonal elements. So this is, for example, 1 and this is epsilon. Then such matrix is non-zero. So how to show this? So what we do, we separate our matrix into diagonal part and off-diagonal part. So if this is greater, then of course this is for surely non-negative. So the diagonal is invertible. So we can take diagonal out, and we have the matrix I plus D inverse S. So the elements of D inverse S are Aij divided by Aii. And what we have the row sum of such matrix. It has 0 on the diagonal, and moreover, the sum of all of diagonal elements in the row is less than 1 in the absolute value. So if you take the first norm, which is the maximum of a row sum, it means that the first norm of this matrix is less than 1. So we have, remember in the Neumann series proof, we had if some norm gives us the norm of the perturbation less than 1. Here we have the first norm. Identity plus perturbation. Therefore, from the theorem from the previous session, again, this matrix is invertible and this matrix is invertible. So that's what we have. A strictly dominant matrix is invertible. And therefore, what we need to show that if lambda lies outside all of the circles, the matrix A minus lambda I is strictly diagonally dominant. And this is what clear from the definition of the circles. If the eigenvalue lies outside of the circle, all of the circles, then you have strictly diagonal dominant property for every, and then this matrix is strictly diagonally dominant, then there is no eigenvalue. So all the eigenvalues lie in the union of circles. A less trivial statement, which we are not going to prove here, is that if the circles do not intersect, the eigenvalues also do not intersect. Yeah.
Shouldn't be there HGG because it should be greater than the sum of all other diagonal elements or all other elements in the same row.
In the same row.
In the same
So the diagonal element is greater than all the elements in the same row. Well, if you look, for example, triangle matrix, so there is lower triangle. It's strictly okay. It is no. The triangle is not strictly diagonal. Sorry, but this is the case for this eigenvalue. Solutions of circles. Yeah, so we can draw. Sometimes you get useful information. So, for example, like this. I don't see it clear. See, but often, for example, but in some cases they don't provide any real information. So, for example, if you have all the diagonal elements that are equal to the same number, then all the circles will have the same center and so on. So they work only, they give useful information